Hello everyone, and Mithun Reddy from EC. My topic is antenna arrays in the time domain and introduction to time arrays. The term phased array comes from the time harmonic or steady state analysis of antenna arrays. These arrays use phase shifters to electronically steer the main beam. Phase shifters catch beam squint and pulse dispersion for wideband signals. So time delay units are needed to correct these errors. Adaptive and reconfigurable arrays also have time-dependent responses. In addition, dependent spurious signals arise due to nonlinearities in amplifiers. This article presents several time-varying issues related to antenna arrays. This could not be modeled by the time harmonic representation of an array. Future antenna arrays will be wideband and time varying. So antenna arrays will have to be designed in the time domain. Background. Traditional electromagnetic analysis converts Maxwell's equation in the time domain to a narrowband single frequency time harmonic. The time harmonic from steady state derivation eliminates time dependence from the equations. Phased array theory spawns from time harmonics electromagnetic fields which fails to appropriately represent wideband signals are fast changing events. Even though wideband arrays and adaptive arrays are time changing, they are still usually analyzed from a steady state point of view. In the literature, wideband arrays generally refer to a wide system bandwidth with a narrow band signal bandwidth. Future arrays must address very wideband signals as well as nonlinear behaviors, adaptivity, and reconfigurability. Bandwidth comes into two variations instantaneous bandwidth and system bandwidth. Signal bandwidth consists of the maximum range of frequencies within the signal incident on an array, while the system bandwidth means that the hardware can process signals with frequencies within that bandwidth. Array system bandwidth is greater than or equal to the signal bandwidth. The primary design factors contributing to the array bandwidth include bandwidth of these elements in the array, element spacing, maximum scan angle, and array size. Phase versus time. Before constructing phased and timed arrays, let us explore the term phase and time. The two modifying words. We frequently see phase and time in the argument of a sinusoid sine of 2 into pi into f plus gamma, where time t as units of seconds and phase t as units of degrees or radians. Time converts to a distinct phase by multiplying by 2 into pi into frequency. But the reciprocal is not true because phase is modulo 2 into pi while time is linear. Thus, gamma equal to 2 pi ft, t equal to gamma by 2 pi f plus n into 2 pi. The array bandwidth fraction of the center frequency as a function of the number of elements in and the steering angle. This reciprocal relationship between time and phase becomes critical for time varying and wideband systems. A single sinusoid has three phase terms in its argument. Sine of 2f 2 pi f of t plus td plus gamma is equal to sine of 2 pi ft plus 2 pi f td plus gamma of s. Assuming a constant time delay td and the constant phase shift gamma is, Phase terms A and B differ because A depends on frequency, but B does not depend on the frequency. As a result, when frequency changes, B remain constant, but A changes. Phase versus timed arrays. A receive linear phased or timed arrays with elements spaced dx apart as a narrow band. Response known as array factor. AF array factor equal to summation of omega n e to the power of j 2 pi f by c into n minus 1 into dx sine theta plus gamma n, where the beam steering phase is gamma n equal to minus n of n minus 1 into 2 pi fc by d dx sine theta. This phase points to the beam to its center frequency fc. Arrays of antennas are used to direct radiate power towards a desired angular sector. The number, geometrical arrangement and relative amplitudes and phases of the array elements depends on a regular pattern and must be achieved. Once an array has been designed to focus towards a particular direction, it becomes a simple matter to steer it towards some other direction by changing the relative phases of array elements. A process called steering or scanning shows some examples of one and two-dimensional arrays consisting of identical linear antennas. A linear antenna element, say along the z direction, has an omnidirectional pattern with respect to the azimuthal angle. By replicating the antenna element along the x or y directions, the azimuthal symmetry is broken. By proper choice of the array feed coefficient an and the design gain pattern can be synthesized. The most break property of an array is that relative displacement of antenna element with respect to each other introduces relative phase shifts in the radiation vectors, which can then act constructively in some directions or destructively in others. This is a direct consequence of the traditional phase shift property of Fourier transform. A translation in space or time becomes a phase shift in Fourier domain. Array steering. The time domain version of array steering is AM modulation, in which a baseband signal is translated up in frequency by modulating with it a sinusoidal carrier, much like frequency translation is also used in DSP for mapping low pass filters into a band pass one and for designing filter banks. We will use it in design arrays with angular sector patterns. And the conclusion is the article explains the growing need to model antenna array in the time domain rather than typical time harmonic form. Phase is a narrow band concept that needs to be replaced with time formulations that are not only hardware based but also signal based. Future wideband arrays must handle wideband signals and not just narrowband signals in an array that operates over a wideband bandwidth. The term phased array appropriately described antenna arrays until recently. The advent of the outstanding time domain modeling software, advances in signal processing, and new hardware technology promise an exciting future for antenna arrays. Thank you.